Pergunta ele. Deve saber. Eu tenho aqui.
Não vai ter isso, mas tem. Você vai ser trouxinha. Vocês vai ser trouxinha. Vai de quê? Ou trouxinha, daquela da mama? Não, muitos gringos. Essa é a marca registrada dela.
Viemos aquí pelos efeitos especiais.
Posso fazer.
Pagador à vista.
Five sharp.
Brazilian.
German
Yes.
Em Bahia.
Você está gravando.
Hã?
Você sabe que na última conferência que eu vim aqui, a conferência começou 5 minutos antes do tempo.
Vou editar aqui.
Ah, pois é.
Sério, foi aqui.
Sharp, por conta do...
Exatamente.
Que alguém reclamou que chegou, que começou antes, 7 minutos. É, ó o charme lá. Chair. Lourenço. Bom. It's a pleasure to be to announce to present Daniel Ismana. He was also a student of Wellington, but he is not here only because of this, but because he really is very good mathematician. Like Pablo. Yeah. And he will talk about atomic decomposition and the transfer operation.
Thank you, José. It's a great pleasure to be here. Can you hear me or fine?
Louder.
Okay, it's a pleasure to be here. I'd like to thank the organizers, especially because I'm coincident of Wellington. So I thought a little bit this morning about what to say about Wellington. I started to cry. So maybe I'm good. So one thing that everybody knows that there is this article about the unraisable effectivities of mathematics in nature of science. I don't know if you heard about it. And I wanted to talk about the unraisable effectivity of Wellington. He helped to nurture so many talents. Because you heard here that maybe the students are a little afraid of him because of the grades and things like that. You heard Newton say that even Wellington make jokes about it. He doesn't have a hair, right? But I think he was a very passionate person. That means that he has very strong emotions. Every time he says something about politics or mathematics, it was always very emotional, or not positive or negative way. We don't want to be in the negative side of this, but always very emphatically positive when he wanted to give a compliment and things like that. And I think he transmits that in his lectures, in his talks. When you heard Wellington give a talk or a class in UFBA, the students feel this love for math, this passion for math. And yeah, the way to stop here. So, got a cold like the blue. So I'm talking about ergodic theory of expanding maps. So let me first tell you something about a boring stuff first, and then to motivate the more complicated, the real topic of this talk. Okay. So let's pick a expanding map of the circle, like this. So pick a F from S1 to S1. And let's suppose that's very wonderful. So it's is an expanding map. The derivative is bigger than 1, and f is C2. It's a pretty boring stuff at this age, okay? And we know a lot about these maps, right? So if you see the interval, let's say, we have something like this. It's a Markovian map. So you have three main properties here. First is expanding, the derivative is bigger than 1. Second is Markovian, so preserve some kind of partition. If you take the partition defined by these two intervals, this partition is invariant by the action of this non-consistent, so this is a very nice property. And it's very regular, it's a C2 map. So the way here is to weaken these two assumptions, Markovian and C2, and try to get results similar to the results that we get for ergodic theory in this set. So the first thing that everybody knows about these maps is that there is a unique invariant probability that is absolutely continuous with respect to the Lebesgue measure. So this measure is just density times the Lebesgue measure. So it's of n. Okay. But you know much more about these measures. Actually, you know a lot. This map behaves in a very random way. So my next slide is the commander in chief, or the elephant in the room. So how you justify all these nice behaviors of these dynamical systems? First, this dynamical systems has exponential decay of causation. Correlations for Holder functions, other kinds of functions, but Holder functions. You have a central limit theorem. For Holder observables. You have the uniqueness of the invariant uniqueness of the invariant measure, of the invariant probability. That's absolute continuous with Lebesgue measure. You have analyticity of the topological pressure. That's amazing to thermodynamical formalism and to understand the geometry of invariant sets, Gauss dimension, things like that. So this is a wonderful tool. And you also have linear response. I need to say linear response. Linear response results for these kinds of maps. Say again? Yes, so yeah. Let's put C just to be sure. And okay. And what is nice is that all these factors can be studied studying just one object. So, and this object starts with L. It's not modular. It's the Ruel-Perron-Frobenius operator. Frobenius operator L. So if you study the action of the Perron-Frobenius operator L in the space of the Holder functions, you can get all these nice results. I'm not saying that you can reduce all these results just for that, but let's say this is one of the main steps. Okay? If you understand that the action of the Perron-Frobenius operator on the Holder space of functions, you can deduce lots of things. Some of the things is very easy from the spectral properties of these, like exponential decay of relations, or maybe uniqueness of this guy here. That's something related to the dimension of the Diagonal space of one, of the Diagonal one. This is not so obvious. It's a little more complicated. This is really more complicated. But there is some standard techniques from analyzing this operator and get these things. It's not immediate, but you can obtain these things. Okay, so that's my first observation. So I'm sure that you know what the Perron-Frobenius operator is. So where the Perron-Frobenius operator is. So suppose you pick some differentiable function or piecewise differentiable function, C1 piecewise differentiable function in a manifold. So if you, the classical Frobenius operator is like this. If you take observable integral function psi, so if you calculate this L on psi, and if you want to calculate the point x, this is just, you pick all the possible pre-images of x, and calculate this. You pick the Jacobian of this function, y, the modulus of this, and psi 1. Okay? So just for this definition, you can easily deduce that this preserves.
Daniel, excuse me.
Yes.
Change the.
After.
There's the pen. Okay, need to change
Great.
my hand actually. So L1, this operator L, preserves the integrable functions. Let's suppose this is the compact manifold, let's say. Okay. So this preserves the integrable functions. And this is the Frobenius operator. But there's a more general versions of the Frobenius operator. And we can do like this, so more general. I'm not going to explain why this is important, but if you know something of this, probably you understand why. I don't have time to explain. So suppose you have some functions also in a manifold, so you have a countable set of, or maybe finite set of functions. So these are subsets of the manifold, and you have an image in the manifold. And these usually are contractions.
So if me is an absolutely continuous measure, and with density C, this is just the density of F star.
Yes, it's just the density of the push forward of the absolute continuous measure by the action of the Frobenius operator in this case. Okay. Okay, so if you have contractions in this manifold, in different sets of this manifold, you have some functions Gi, also defined in the same set with values in C. Then you can define a more general Frobenius operator that's like this. The sum of all the contractions, Rx and psi, like this. Okay? Of course, in this case,
yeah, writing that behind the barrier. It's not the barrier of potential.
I see.
The barrier of potential is.
So here is writing psi, Gi, and Phi. Okay. It's a glass.
The glass is not the problem of the beta.
Okay. Good. So that's the Frobenius operator. And what kind of properties that are nice to define all these properties of this body in dynamical systems that you see here is the quasi-compactness of the Frobenius operator. I mean, it's not the only one, but it's the most, usually it's the most, I think it's fair to say that's the most difficult property to obtain. So let me explain quasi-compactness. Of the Frobenius operator L. Okay, so if you understand, if you wanted to, for instance, if you wanted to understand linear response or the analysis of topological pressure, what you need is to understand what happens with the eigen functions of the eigenvalue 1. So when you perturb this dynamical system, you have a family of Frobenius operators, and you want to see how these eigenspaces change when you change the dynamical system. Okay? So it's nice to understand very nicely how is the spectrum close to the eigenvalue 1. So that's the main thing. Okay? So it would be wonderful if you have this situation, so ideal situation.
And the first definition you have an eigenvalue 1, the second one is not clear.
Yeah, here is not clear. So I'm going to emphasize this one, otherwise I need to be more careful about this. Okay? So in that case, eigenvalue 1 is kind of special. Okay? So what would be nice is have a situation, have a Banach space of functions, where the action of this Frobenius operator is like almost like infinite dimension. So you have a finite number of eigenvalues, and that's it. Okay? All the spectrum are just eigenvalues. For this is very unlikely. What you can have sometimes is a compact operator. And in this case, you have a countable number of eigenvalues. 0 is here. You have 1 here, that's, in this case, is the eigenvalue that you are interested in. And maybe you have another ones, and if they have an accumulation point, they accumulate at 0. You can have infinite many, but they accumulate at 0. But this is very rare. You don't have this. This happens sometimes when you have a real analytic dynamical system. That's very nice. So if you have a real analytic map like this, you may have this. You have this equation. So, but it's very rare. So just people that are not very smart, like Joel or Botenic, that works with compact operator, right? So it's unlikely to happen. Okay. So we're just ignore this. So one question that you may, if you never thought about these things, is why you don't consider the space of integrable functions? Okay, you can consider the space of integrable functions. In this case, this is a bounded operator, but the spectrum is very bad because the spectrum, I don't know how to prove this, but it's the whole unit disk. So the spectrum of this operator.
In which case?
For instance, in the case that the trivial case that I consider, okay, so the whole case. So the essential spectral radius coincides with the spectral radius. So 1 is here, but it's not an isolated eigenvalue or something like that. It's terrible, okay? Because you wanted to perturb these and see what happens with the eigenspaces here. It's not an isolated eigenvalue. So this is terrible. So you have weird stuff here. Weird stuff. That's not the technical term. And why you consider the Holden function, the space of Holder function? You consider the space of Holden function, but over here you have a bounded operator too. But you have weird stuff, but the weird stuff is away from the unit circle. So you have 1 here. Here 1 is an isolated eigenvalue from this, and the rest you may have some finite number of eigenvalues here, and then you have the weird stuff, but the weird stuff is far away. Weird stuff. Far away of the unit. So that's the ideal situation to obtain all that.
Unit circle.
Say again?
Unit circle.
Unit circle. So unit circles here. So all this weird stuff, the essential spectrum, so the technical term, the essential spectral radius, the part of the spectrum that's weird, is far away. So you have a definite distance from the unit circle.
Are still talking about expanding maps of the system?
Yes, exactly. Okay, so in this setting you have this. So this is quasi-compact. Okay, basic. So another way to see this is that you can decompose this operator in 2 parts. L1, this is not so obvious, but you can decompose this space in 2 parts. A contraction on the space of Holder functions plus a compact operator. It can be, for instance, a finite rank operator. Okay. Okay. So that's the situation that you want. Once you have this picture, all these things, I mean, it's not immediate, but all these things somehow get much easier to detect. Okay? Not trivial, but need to work a little bit. So the goal of this talk is to domain the beasts. So the beasts are maps that are not so nice as the maps I described in the beginning. So let's talk about these dimensions.
And it will be in the one-dimensional context, or in
No, multi-dimensional. Yes. So I think it's going to be clear now. So the beast lives in a lot of places. So first, the monsters. One monster that is Keller helped to understand in the beginning was C1 plus alpha piecewise expanding maps. As piecewise C1 plus alpha. Piecewise C1 plus alpha. So this is less regular than C2, and also is not Markovian. So it's expanding, but does not suffice two of the properties. Another one that's bad are Lorentz maps. So Lorentz maps are maps where you have, they're expanding, but there is a point, for instance, where the derivative explodes. The derivative of this point at this guy is infinity. So this is really bad. It's not Markovian here. But there are Markovian maps that also are difficult to understand these ergodic properties that I described here. For instance, you can pick a unidimensional map with infinitely many branches, and these branches, the image of these branches are very small, decreasing very fast. Okay, like this. Okay. So that's a really bad situation. Even if this map is expanding, in some cases, this does not have absolute continuous invariant measure. Okay? Actually, when you wanted to understand the existence of the wide attractors that Sebastian and Hank and Wiki did, you need to study this kind of maps. Okay? So that's really bad. But
including that the case when it sends everything to zero?
sends everything to zero. So this is going to zero.
Yeah, but the rest, I mean, sometimes you are...
No, I cannot. So this is a situation where I cannot state for all maps like this, because some maps like this, the direct measure supporting this point is a physical measure.
Yeah.
Everybody converts there, so this is bad. I cannot deal with this
And
situation.
the other question, if Lorentz remains bad from your point of view, so it is Markov?
Yes, I think it's also bad. Yeah. But I'm going to deal with no Markovian. Okay. So Armando asked me if I can consider multimodal maps. So yes, I can consider multimodal maps. But again, not all multimodal maps. There is a gentleman Bazzi and Suji studied very well these kinds of multimodal maps. Some of them does not have absolute continuous invariant measure. So you should be careful about this. But I wanted to consider also try to study some of these expanding maps, let's say in a square, like this. So I have many pieces. Okay.
Sorry, Daniel.
Yes.
You mean multimodal or multidimensional?
Multidimensional. Sorry.
You wrote multimodal.
Ah, yeah? Okay. Well, you know why. Multidimensional. Okay, so let's say piecewise. Infinite. Okay. So in this case, you have a map like this, defined by pieces. In each one of these is like infinite, or infinite. And this guy grows like this. So you have a metric expanding map. So you have like a metric expanding map. This is also a difficult situation. I'm going to see to give you the proper reference if I have time.
But also maps induced by multimodal maps?
Yes, so probably this kind of multimodal maps these kinds of maps can be induced by multimodal maps. Right? Okay. For unimodal maps, so unimodal maps, like the Fibonacci map, where maps like this appears when you take production. Yes? Okay. So let me just go for one more example that probably is the worst of all. That are the fat solenoidal attractors. So and I think it's easy to understand why they are bad. So fat solenoidal attractors. So in this case, so I think Suji gave this name for this. Right? And he studied this kind of maps. So you have a map from S1, so it's a ring, right? So it's something like this. Annulus. It's a annulus like this. And you have some lambda that's, let's say, an integer, could be 2 if you want. And have alpha smaller than 1. And you define this kind of skew product. Mod 1. And here you have some smooth function, let's say phi plus alpha. And like this, okay? So in this case, you have expansion in one direction. In this direction you have expansion. In this direction, in the direction of a little bit like y, you can have contraction. Okay. So the Jacobian of this, I hope so, is lambda alpha. And let's suppose this is the bigger one. So in this case, you have that small ball. The image of a small ball is not a ball; it's kind of a more elliptical shape. But the measure is bigger than the original ball. So this is measure expanding. But it's not metric expanding. Okay, so this is worse than that situation. So I wanted to obtain results like for expanding maps of the circle, for this kind of map. Central limit theorem, exponential decay correlations, and things like that. So there's a long story about these maps.
Yeah, but in this case, attractor can have non-empty inclusion.
Yes, exactly. So you can ask this platform attractor, what's the structure of this? Okay. So if this, this depends on this 5. If this 5 0, you don't have absolutely invariant measure. So it's really bad. Okay. So okay.
So you have a lot of moral judgments on this situation.
A lot of what?
Moral judgments about what's good and bad.
Oh yes,
Okay.
yes. I'm sure Wendy would give a very strong opinion about it. Has a very strong opinion about that. So, yeah. But you're right, yes. It would be nice to understand all the situations.
What you really mean is that these are all good because they're much more interesting.
Yes, yes. They're very interesting because I'm doing something about that. Okay, so there are a long story about this. So the idea is to find a Banach space where the action of the organism operator is acting as a quasi-compact operator. So maybe the first, well, there's a long story starting with Gauss. If I start with Gauss, I'm not going to finish the talk. It's very interesting, but I'm not going to finish the talk. I'm trying to do introduction for the paper. You can imagine how difficult it is. But let's just start with laws of New York, okay? So if I start with laws of New York, and Gauss. So you have laws of New York that consider the setting of piecewise, I think C2 maps, maybe a little more general than that, I don't remember. And they prove the famous laws of New York inequality for this kind of maps. And I suppose they don't get all the consequences of this, but you have Keller and Hofbauer. I get the consequence of this laws of New York inequality for this setting. And then there is also Bora, I don't know how to say his name, that proved this was C2 expanding maps, multidimensional. But it's kind of different from the other situation because this kind of results we are very used it in one-dimensional situation that you get these results about exponential decay correlations and quasi-compactness. In every situation, just say something about the regularity of the map, everything's fine. But in this situation, you need some estimation to get the quasi-compactness. So it's not that maybe it's not that nice, but what you're going to see is a little inevitable in this segment. Okay, so maybe the next one I want to talk is about the Banach space of generalized.
Compactness, there's the middle situation, bounded plus compaction. Contraction.
Yes, exactly. Yeah, that would be the definition. Okay. So generalized p-bounded variation space. I'm not going to give the definition, it's kind of long. So these are introduced by Keller to understand this equation. Piecewise one. One dimension, okay? But then a lot of people use this same Banach space to understand multidimensional situation. And we have, I don't know how to say that too. So, and Suji Probably I'm going to offend someone that's not very against, so I suppose it's fine. So, it's not in the audience, so it's fine. And lose independently. So, this is for piecewise locals of multidimensional. And then there is this amazing result independent by Tsuji Buzzi about piecewise real analytic. Two-dimensional, I don't know, right? Two-dimensional, okay, two-dimensional. And this is one of the few results that is estimate-free. So you just say something about the regularity of the map, and then you get the absolute continuity by the measure, and all the nice results. So this one is not like a difference between these results. Okay, how much time do I have? An hour? How much do I have? Pacific is not here. Half an hour. Okay. Okay, good.
No, 20 minutes. Sorry.
Okay. So,
There's also cohesion, right? But you don't have to write it on the board.
okay, I don't know how to write.
Cohesion.
So, now, they're recording this, so it's not a good idea to do it. Okay, and I have the fat solenoidal attractor. So, the next, so this is not an evolutive story. I'm not saying this is better than this or something like this. And, but now we have Sobolev spaces. And this was, I suppose that was first applied by Tsuji, and then Avila, Rosell, and Tsuji. In the fat solenoidal attractor case. And there's also a result of Tomei for piecewise. So in this case, you don't have discontinuities, okay? You don't have discontinuities in this case. In this case, you have you can have discontinuities. So piecewise smooth maps on surfaces or
Any dimension.
any dimension. Multidimensional. And this is kind of inspired by, so there is a parallel history in the piecewise hyperbolic case or hyperbolic case. That actually is a very hot topic. Two main contributions, lots of contributions of this in the audience. And this was inspired, I suppose, in this hyperbolic set, for this hyperbolic set by Balaji. This is after Balaji. And so I forgot to say something. This is joint work with Alexander Abieto. And I need to say this because he's seeing this in the YouTube. Probably he's already sent a message. Okay. And finally, you have, maybe this is not so known as these examples. That is the case. Alexander Abieto, it's very easy to remember. Okay, so there is also, this is, I'm not going to describe what these spaces are, but there are spaces of certain, I need to be vague here, certain regular measures. So this is one-dimensional situation, piecewise C1 plus alpha case. Maybe in one of them, in the Leverani case, is infinite many branches. And in the Oliver Butterley is a finite number of branches in the same set.
Sorry,
Okay?
Daniel. Speaking about that, in the multidimensional cases, it's finite dimension, right? In the ones that the pieces for the piece.
So in this case, yeah, but you can also ask about the infinite many.
No, but the reference that you gave,
Yes,
the ones
I
that are
think
true,
Finite.
the finite dimension.
finite many.
Change.
Okay. And think Suji is also finite. Okay. Good. Okay, I need to see one more start. To talk about references. And two more actually. One of them is standard pairs. So that's very new actually. Standard pairs in this setting. So this is not actually a Banach space like a Konya function. So this standard pairs, as far as I know, was developed by Chernov and Piaf. Also for the hyperbolic setting, but I think this is Islami.
Yep.
Yes. Islami. And Islami. So he's adapted for expanding maps on metric spaces. Okay. Okay. And finally, a very, very recent result for Bezoar spaces. So in this case, so for smooth expanding maps on surfaces, it's a multi-dimensional setting. So no discontinuities here. They did actually pick a more general dynamical system and try to prove into there. They put a very classical expanding map on a surface and a variety, and prove that you have these exponential calculations, things like that, for Bezoar spaces. Okay? Okay, so this is Macrophylla and Sakam. So this is very, 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 these two are very recent. Okay? Okay, so what I wanted to do is to do the following, to give you yet another Banach space. So the next section is, no, yet another Banach space. So it's funnier when Travis says it. So, oh no. Yeah, another Banach space. But actually, that was the translation. I was very envious of Ian because you always invent new Banach spaces. I wanted to invent my own. Okay? So the question that you consider that is why to give another Banach space, right? So the selling points are the following. I'm going to try to sell my fish without trust the other ones. Okay? So because the goal, I think, is different from this one. So, for instance, in this kind of Sobolev spaces, we want to find some spaces where we have a very good control of the weird part, the essential spectral radius. That's the goal. So they actually pick very small spaces to get a good, more smooth functions to get a good control of the spectral radius. So the first selling point is that the Banach space, I'm going to give you the full definition of the Banach space. So the Banach space has very elementary definition. A very elementary definition. Two, that's a very large space. So that's the best selling point. It's a very large space. For instance, it includes the Keller space, the Keller of P. Generalized P-bound variation includes Keller spaces. That's probably the most famous approach for this kind of thing. Space.
Daniel.
Yes.
Time to change the.
Again?
Okay.
Another
Let's
thing.
use everything and we need to get
There's another thing.
Red and black.
Good. And so this is also very nice. That in many situations, this space coincides with the Bezoar space. So in many situations, this Banach space is exactly the same depth of Bezoar space. very low regularity. And maybe this one is also very motivating. You can consider potentials that are Bezoff. Okay? So people consider Holder, piecewise. Yes. I'm going to give you the definition in the last 5 minutes. Don't worry. So, but it's a very famous scale of Bond space. There are like thousands.
People in the room, we forget.
Say what?
There are old people in the room, we forget. I forget.
Yes, but I don't know the definition, so that's why I'm going to put my definition that's more simple. That's why. That's the other selling point. Remember, very limited definition. Okay, so this is not a free estimate statement. Okay. We need some estimation about the potential together with it. And another thing that's a unified approach for all these segments.
What do you mean by not free
So like in this case, you don't need to know anything about this. The Holder norm of the potential is automatic, right? And you need to know something about the Bezoff norm of the potential. Okay, now I'm going to give a definition. Okay? And as we're going to see, it's very easy. I don't need any differentiable structure. I don't need any metrical structure to define this. So it's a purely measure theoretical set. And this is very nice. So the next section is called building walls. This is very popular now. It's a very popular topic. I wanted to see this. Okay? Let's do the beautiful wall. Okay? So pick a probability space. Probability space. And I need additional structure. And this additional structure is a sequence of nested partitions on this probability space. So I have partitions, it's a sequence of nested partitions with bounded geometry that I'm going to explain here. Okay, so let me illustrate this in the very simple case that's the interval. So we have the interval 0, 1, and so this is the initial partition, contains just the full space, and then the next partition you have 2 elements. You don't need it to be exactly in the middle, something like this. So that's 1, and then you have the next one. You can subdivide in the, let's say, 2, this one, 3, this one. You have the next partition, so on. Okay. And what I mean by bounded geometry?
So one is a refinement of the other.
Exactly. Exactly. A sequence of refined partitions. I lost the. Where is it? It's a sequence of refined partitions. All of them are finite. And by bounded geometry, I mean just that the child. So this is kind of this is like a child of this one. So this one cannot be very small compared with the original one. And also cannot be very big. Okay?
In terms of measure, just.
In terms of measure. Just measure. Don't have metric here. Okay? So there is some. So what means by bounded geometry? It means the following. There is 2 numbers, 0 and 1. So that if I pick some P in this partition over K and pick a child of this in the next level, then you can compare the measures. So the measure, so I'm going to use this notation for the measure, okay, just to simplify the notation. So this is the measure of K. Okay? Over P, this is not very large, it's not very close to 1, and is also not very close to 0. So this is bounded geometry. Okay? So example that you have in mind, probably you already imagined that. Take the diagonal partition, the sequence. This is a classical example, sequence of diagonal partitions on 0. Okay? Okay. So now I need to define something that are the atoms. So the approach to define this Banach space is called atomic decomposition. Okay. So what is atomic decomposition? You describe the functions in your Banach space as a combination of very simpler functions. Okay? This representation is not unique. It's not like a basis. Okay? Not like wavelets or something. It's more flexible. Okay? So to define this, I need to define what is SP Souza atom. Souza is a Brazilian mathematician. I have time to explain. And S is going to be a number between 1 and P0, and P is going to be bigger than 1. Okay? Eventually, your Q is going to occur. It's going to be bigger or equal to 1. Okay, so what is atom? The atom supports, so pick an element of the partition. Pick an element of the partition. So an atom supported on this element of the partition is just the characteristic function of this element times a number. Okay? So it's just a brick, and this height is the measure of Q, S minus 1. Okay? So it's just that. So this is a function AQ, and AQ is just x is just 0 if x does not belong to Q, and is equal to this number otherwise. Okay? So it's a very simple function. It's a characteristic function times some number. So that's the atom. So you can easily see that if you pick the example of the intervals. So the atom of the whole thing is something like this function. So it's a fat guy, right? So this, but very short. And if you pick some Q that's very small, because this number, this guy is negative, is very high. So it's a guy that's very tall and very thin. As you can see, I'm not an atom, because I'm tall and fat. So the bill to be atom, okay? I don't fit the bill to be atom. Good.
So we call
Now,
you a molecule.
What?
We're going to call you a molecule.
Yes, exactly. Actually, there is this terminology in atomic decomposition.
Okay, good.
Yes. Very good, you know a lot. Good to have an informed audience. Okay. Okay. So, I'm going to define the Bezold space. How much time do I have?
It's my 5 minutes.
We want to know. We're sitting on the edge of our seats.
Okay, right? Don't ask. So, the Bezold space associated with the structure is just a probability space in the sequence of partitions. Okay? Just that. So this Bezold space belongs to LP. Actually, you have a compact inclusion. And you say that a function belongs to this Bezold space.
So the sequence of partition is fixed.
It's fixed. Yes. For every partition, you have a space. Actually, it's very sensitive to the partition.
Every sequence of partitions.
The sequence of partitions. Yeah.
So do you have an assumption about how this asymptotically or how you need anything?
No, it can be totally crazy, yes. Can be totally crazy. But the space is sensitive to the sequence of partitions. So if you change, okay, so remember these assumptions here. So you say that phi belongs to this if and only if there is some sequence of complex numbers, and that are indexed by the elements of the partitions. Okay? For every element of partition you have a complex number. And in such a way that phi, you can write as the sum of linear combinations of these atoms. So you pick an atom supported on Q, and multiply by some number, and this is a linear, so this is finite series, this one is a finite sum, and this is a series, where the cusp of this representation is finite. So the cusp is defined the following way. You pick all these coefficients and make the following calculations. So you pick just this to the power p. So for each level k, you pick the LP norm of the coefficients, and then you sum of all levels. You put a k q here. Okay. So this is the cusp of this representation. So if this is finite, I can prove it's easy to prove that this converges on LP. And this is LP. Okay. So this is the space where the cusp is finite. Good. So now you define the norm. So this is typical of atomic decomposition. You represent the function as a combination of the atoms, and say that the norm is the infimum of all possible cusps. There are many possible representations. So you take the infimum of all possible cusps, and this is the norm of this space. So the norm of this space, is just the infimum of the cusp over all possible
Tough to compute.
Huh?
Not easy.
No, the exact value of this info is not easy to compute, but it's very easy because these functions are very easy to understand. It's very easy to specify if a function belongs or not. Okay. So the case where P and Q is equal to 1, this is exactly like built a wall. So you have these bricks. So there you have a company that constructs bricks like this. And you have the function here, the function psi. I suppose that the phi is positive. So we have a wall. And we are going to build a beautiful wall with these bricks. So we put the bricks here and try to fill this wall with these bricks. Okay. But the analogy is not very nice because you can consider negative bricks too. So, okay, I don't have time to the story. I wanted to finish this because you look tired. So I wanted just to give an idea why you have quasi-compactness in this space. So the definition is very simple. I think I convince you that the definition is very simple. But I wanted to prove.
You have quasi-compactness in which hypothesis or which kind of dynamic?
Fortunately, I'm not going to have time to say that. Yes. So in this level of generality, what I can say is the following. You can apply, for examples, each one of these pieces that I gave you. So Lorentz, piecewise one, in the Keller case, it's 1 plus alpha. You can apply in all cases, define the number of partitions. In Lorentz maps, you can apply. For multidimensional settings, you need some estimation about the norms and things like that.
These partitions are constructed depending on the dynamics?
So if it was internal maps, the best choice probably is the dyadic sequence. In this case, you get exactly the Bezout space. So if you pick
Independently of the actual map? You just take that?
Exactly.
Independently of the map?
Independent of the map. So in the case of when it's Markovian, you can sometimes choose the second dynamical partition. It's easier, right? But if you pick the dyadic partition, you get the Bezout space. So it's better, right? Because it's a known space, a nice space. Okay, let me just give you, to finish, an idea about how this works, how you get contraction. It's actually very easy to explain in this simple situation, right? So in this situation, I'm going to explain to you. It's a little disappointing, right? But I'm going to show to you the main principle to get the contraction. So in this setting, I'm going to put the dyadic partition. And I'm going to do the following. I pick an atom that is not the full support, is not the full interval. Okay? So pick an atom in the sequence of dyadic partition. But Q is different of the whole. So in this case, the action of the Perron-Frobenius operator on this atom is very easy. So if you pick the Perron-Frobenius operator and apply to this atom, you get the measure of the atom. So this is the Lebesgue measure times 1 2, and you get 1 over 2, 1 minus 1 over P minus S, and you get the atom of 2. This is the image of this Q by the map F. Okay, so pick the image of the Q by the map F. So you get the image of atom is a fraction of atom, because this is smaller than 1. This is smaller than 1. Okay? So if the atom is not the whole thing, you get contraction. It's very easy to verify that. So what you do is, so in the case that's simpler to explain this case, you just pick a representation of phi, of a map phi that's very good, of a function phi that's very good. And you apply the Perron-Frobenius operator to this map, to this function, sorry. So you have this part that you don't know exactly what happens in this case, actually. Just this atom that you don't have contraction, you just put this apart, and this is finite Hank operator. And the rest is these guys, with k either equal to 1. And each one of these atoms are contracted by L, so this is a contraction. So that's the idea in the case of piecewise linear case. Okay? And in the general case, it's more complicated because the image of atom is not exactly atom, so you need to control this in a best way. I think I don't have more time. We'll have more time, right? So before to finish, let me say that Lorenzo wanted to talk about the what's about?
It's Luna, in fact.
Luna. Yeah. Luna wanted to talk about the Rede Nacional de Pesquisa with the Brazilians.
After the talk.
After the talk. So stay after the talk.
The people interested. The Brazilians interested.
Yeah, Brazilians one. Yeah. Okay. So thank you very much.
So what can you say about, this?
Questions?
Was interested.
This kind of thing.
Authority goes to the hell.
What can you say about the density, right? So you have, this is also space in which you will have then the density.
The density belongs to the Bezoff space. So the density belongs to the Bezoff space. But if you have a more regular space, you can know something more about the density, of course. Okay?
But so this density will belong to the space which will, at this point, no longer depend on the partition somehow. I mean, you will end up with something that does not.
So if you're working with multi-dimensional expanding maps in a surface or something like that, you can make a triangulation and make a nested sequence of refined triangulations of the surface, and you get a nested sequence of partitions. And this does not abate, if you are careful, this does not abate too much of the partition. So you pick like 0, 1, you divide by 2, by 2, by 2, by 2, you get the classical Bezoff space. If you divide by 3, by 3, by 3, by 3, you also get the Bezoff space.
But so I guess what I'm saying, in practice to apply this, is it an issue to where is the difficulty? Do you have to construct the right partitions? I mean, what is
No,
involved
the
in
partition
checking?
is not the problem.
It's not the problem.
No, the partition is not the problem. The partition is, the problem is to, apply to, I don't know exactly what your question is.
So how you choose P and Q?
P and Q, the partition or?
This number is larger than 1.
This number here?
No.
The definition.
P and Q. So this depends on the, if you like, if you want it to be simple, if the finite number of partitions, or the map has the domain of definition, the finite number of pieces, probably wanted to pick the simplest case that P and Q equals to 1.
No, but in higher dimension you have this complexity business, and then you will have
Exactly, so we need some estimation about the geometry and things like that to get the result. So it's not an estimation free result like Suji and Jeremy Buzz. You cannot get that unless it's realistic. There is piecewise affine examples where we don't have absolute continuous measures. So you need some estimation.
And the dual of the space, because you need
The dual of the space.
You need after you have the hierarchy, you need, if you want to have a uniqueness of equilibrium state, you need.
So I emphasize here the case of the log of the derivative, right?
Yeah.
But if you wanted to deal with more general observables, then you can consider the dual.
Yeah.
The dual of Bezoar spaces are well known, it's very well described and things like that. But I didn't try to do this. So the quasi-compactness is not about invariant measures, right? It's just about the decomposition of the operator in a certain way. So that's the first step, it's not the last step to understand the derivative.
Should this extend also to the hyperbolic case? I mean, do they have,
Yeah, that's a good question. I don't know.
but do they have description of Bezoar spaces, anisotropic Bezoar spaces in terms of this atomic decomposition?
I don't know because this was never done in this. This was done just in the case of intervals or like domains in the Rn or something like that. And I will see a description of these in the. This is a new definition.
What did
No, but when you say it's equivalent to the Bezoar norm,
So this is
something
equivalent
that
to
you
the
do,
base
or
of.
sorry, is it something that you do or it's a classical result?
So, no, I prove it that if you take a homogeneous space, that is a metric space with a doubling measure, so there's a definition of Bezoar space in this set. That includes the interval or compact manifold or things like that. So in this setting, this point size, if you choose the partition in a smart way, you get the Bezoar space.
I understand, but you claim this is a new result.
This is a new result.
what is this closer to?
So he defined Bezoar spaces in the interval for spatial parameters Q and Q, not for all.
Okay, more questions? After. Thank you. Just 1 minute that Luciana has another announcement for some.
While Luna speaks.
I don't know what is going on.
It's a cultural hint, okay? I'm writing on the board, yeah? And
Alô, sim, funciona, it's working. And I would like to give a cultural hint for you about music here. And I will write on the board, but there is 3 things to do now, today. The first one is Joatan Nascimento at Varanda do SESI, is a theater at Rio Vermelho. He is a good trumpet player here, and there will be a show about chorinho. And Aliança Francesa is happening right now. Mo Brasil is a guitar player, very good jazzist, okay? Quintet, okay? Mo Brasil Quintet is right now occurring, okay? At Ladeira da Barra. And Jazz na Avenida is Avenue Jazz. Dalga Daí and the Strangers, Os Estrangeiros. Inviting Nancy Viegas is a singer from here. Okay, I will be right here, and you look at it. Thank you. Yes, Luna, please come here. Luna is the winner of a mathematician of a L'Oreal prize. Yeah, thank you.
Okay, nothing. It's just that Monday evening we were speaking about organization within Brazil, and speaking with Lorenzo, and we were speaking about this fact that there is the rede brasileira de sistema dinâmico. O Ali está aqui.
Tassili left. He left in the morning.
Okay,
Yeah, so
he is the coordinator, and there was this idea of the fact that maybe we could have some kind of coordinator for every institution in Brazil who wants to be, and if there is a head of the organization, in order for people start to advertise what's going on in Brazil. The fact is that there are a lot of seminars, for example, in Rio. There are a lot of people coming, visiting, but sometimes it's not very easy to share information. And this is really something within a Brazilian problem. So I mean, it's kind of. And
I propose that each institution here in Brazil send to Luna, important to Luna, with the email of a coordinator in the institution, and then that is the first step.
Yeah.
It's institute select someone to be in contact with
Exactly.
you.
Or with Ali, since Ali is the head. I mean, Ali is not
You
here.
will contact Ali.
Yeah. I mean, if I don't know, in some yes.
The information will contain the fact that people are coming ahead of time, so that
Exactly.
the organization of the travel can be done once the people are here.
So if we have seminars with some, say, like, big shop coming from blah blah, it would be very nice for people to know if there is this person at IMPA or at UFB or at San Carlos or at UFB, and maybe we want to go to see the seminar, or maybe we want to send this person somewhere else to borrow. That's it. So the idea was trying to figure out a coordinator for each institution in order to start organizing the dynamics in Brazil.